Now that we have gone through the various features and settings in depth, let's quickly run through another example. Let's choose 1KIM, then click Import. Notice that this structure shows atoms colored cyan, in addition to the red atoms of missing side chains upon import. The cyan residues indicate that the adjacent residue is missing, for example, when there is a missing loop. So, in this case, we'll check on both fill in missing side chains using prime and fill in missing loops with prime. We'll leave everything else on default settings and click Pre-Process, and then Continue and Don't Show Again to confirm we're also running prime to fill in the missing atoms. Now that's done, we'll include the protein before and after, and then tile entries so that we can see the difference. And you'll notice that the loop has been filled in. Keep in mind though that we should refine the loop further with prime later on, especially if this area is of particular interest. In this case, however, we're really focused on the binding site region, so let's just continue. A couple of missing backbone atoms are reported here. Now, prime could only fix missing sidechain atoms automatically, which is why it did not address the missing atoms on these residues. We could either fix this manually with the Maestro Builder, however, because the region of interest for this specific protein is at the binding site region and these alanines are far from the binding site, then it's safe to ignore them for now. There also appears to be some overlapping atoms. These are actually just some of the polar hydrogens on the predicted loop, so these should get fixed later on during hydrogen bonding optimization. Over in the Review and Modify tab, we'll click Analyze Workspace. We have two chains, A and B, and we have a co-crystallized ligand in each chain, as well as some sulfate ions. And we also have the list of waters. Now, we won't delete anything here, but we will run Epic to generate states for the ligand, so let's click Generate States. Looks like the original state has the lowest state penalty. It's neutral, and it makes 3 hydrogen bonds, which we can see here. The second state has a high state penalty, is negatively charged, and only makes 2 hydrogen bonds. So in this case, we'll keep the original state. We'll do the same for the other ligand in the other chain, and just continue on. Here, we'll click Optimize in the H-bond assignment section. Now, optimizing the hydrogen bonding is important because X-ray structures do not usually have enough resolution to fix the orientation of terminal amides or histidines, or the orientation of hydroxyls and thiols. Indeed, it looks like this histidine in the binding site was improved such that before it made no hydrogen bonds, but afterwards the tautomer is flipped, resulting in an intramolecular hydrogen bond. Next, we'll remove waters with less than 3 hydrogen bonds to non-waters. Now notice we are left with a couple of water molecules here, bridging interactions between the ligand and the receptor. This may indicate we have waters critical in binding for other ligands other than this one. However, we won't know for sure right away. At the very least, this critical piece of information should warrant further investigation as to whether we want to include these waters when virtual screening for new ligands, either by running tools like Bioluminate's Consensus Viewer to identify conserved waters for this target, or to use more advanced simulations to estimate the water network and thermodynamics like running WaterMap. Finally, we'll click Minimize to run a restrain minimization to remove atom clashes and relax the sidechain and other modifications made to the protein. Now once that's done, we are left with a fully prepared protein ready for modeling.